Okay, so right now we're going to be talking about these position time graphs in terms of motion maps. On the right, we see a motion map here, and on the left, we have our familiar position time graph, position in the vertical axis and time in the x-axis, the horizontal axis. And so now we're just going to translate this motion from 0 meters up to 4 meters, at rest at 4 meters, back down to 0. We're going to translate all of that action into this little motion map on the right. So the layout that we have here indicates, has all of these marks here, and each one of these marks is a position. So if this whole thing here is going to measure out 5 meters, we can say that each one of these is 1 meter of position. So this would be 1, 2, 3, 4. I'm just going to abbreviate it that way. So all we're really trying to do is figure out where this object is after every second. And so we're going to indicate each second by an arrow. So at 0 meters and 0 seconds, we start here. And so we're going to draw an arrow all the way to the 2 meters, because we can see here that after 1 second, the object has traveled 2 meters. And so now after 2 seconds, we'll see that the object has traveled 4. And so from this point, we can put a little dot here to indicate that arrow is a 1 second interval. And then we can go from 2 meters to 4 in the next second, or second number 2. So that's what's going on after 2 seconds. And so now we see between 2 and 3 seconds, the object is at rest. It's not changing position at all. It's staying at 4. How do we indicate that here on the motion map? Well, we can just kind of do a little down arrow like this to show that we're remaining at 4, roughly there, remaining at 4 meters. Erase this just a tad. All right. So just do something like that. And then over here, it doesn't have to be all like that. You don't have to be all super technical, but you get the idea. So there's a dot after 1 second at 2 meters. And then after the second we're at 4. And so then between 2 and 3 seconds, we just draw an arrow down like this. So between 2 and 3, the object has not changed position. It stays at 4. You can see here, from 2 to 3, it stays at 4. Now from 3 to 4 seconds, it goes from 4 meters to 3 meters. So we're just tracking this coordinate every second. We're tracking every point every second. So from 3 seconds to 4 seconds, it goes backwards to 3. So we can have an arrow that goes back from 3 to 4 and a little dot there. So that's the what happens in the 4th second. And then from 3 meters to 2, does anything happen, in the same pattern? Looks like it does. From 3 meters to 2 meters, next second over, which is from 4 seconds to 5 seconds, it goes from position 3 to position 2. So there we are in the 5th second. And then from the 2nd meter position, from 5 to 6 rather, it goes from 2 meters to 1. So we just indicate that like so. And that's what happens in the 6th. And then from 1 meter to 0 meters, basically the starting point, it travels 1 more second, the 7th second. So we've spanned the entire time here, 0 to 7 seconds. You will, that's 0, 1, 2, 3, 4, 5, 6, 7. So that's basically a motion map. It's just another way of showing motion, just like we do here in the position time graph that we graphed from our data table of position versus time. You know, the dependent variable on the left-hand side, independent variable on the right-hand side, translates to a graph, translates now to a motion map. So this is what you're going to do in this part. You're going to go backwards. You're going to go from a motion map to a graph. So I'm just doing this backwards. I will let you describe the motion in your own words, but I will give you a pointer as to how you could describe the motion. So one thing we want to keep in mind, or one thing that is true about the slopes of position time graphs. So these lines here, you can take the slope of these lines, you can take the slope of this line here. And one thing, you can write it here on the CVPM or in your notes, but the slope, one thing about this slope here, the slope of a PT or position time graph is what we call the average velocity. So on page 3, when it was asking you to find the slope, that's the math. You know, we've been finding slopes for a good long time in algebra, but in physics, that slope translates to a velocity. That slope is a velocity only for position time graphs. When we go to velocity time graphs or any other type of physical quantities, the slope quantity changes. But for right now, where we are, the slope of a position time graph is the average velocity. So then you can say that, oh, what's the motion? Okay, well, the slope here is going to be constant, something like that, or it's a positive slope. Well, we know it's a positive slope. So we can say something like, okay, if it's a positive slope, then it has a positive velocity. Car or object has a positive velocity from 0 to 2 seconds. Then it's at rest, and it goes back the other way. So anything you want to describe the motion of this object in your own words, I'll just leave that for you. So just give me your pointer. But from 0 to 2 seconds, right here, 0 to 2 seconds, that is a positive slope. And by definition here, that means that the velocity is positive. That means you have a positive velocity from 0 to 2 seconds. You have no slope here, therefore you have no velocity. The object's at rest, it's not moving from 2 to 3 seconds. And then from 3 to 7 seconds, it's going back the other direction. It has a negative slope or a negative velocity, which means that the velocity is traveling towards the west. It's going the other way as the object is going the other way. So they're both in the same direction there. So of course, on this position time graph here, the positive numbers indicate an easterly direction, and underneath the x-axis here, underneath this 0, if we were to extend this, that would be the west, and the time would just extend out to infinity, if possible. So that's what we have. I'll leave this for you in your groups, or for you to complete individually. All right. Now, page 5, we are going to take a look at this position time graph and answer some questions related to it. So let's consider the position versus time graph below for cyclist A and cyclist B. So we can now say, answer this question here. Do the cyclists start at the same point? And we can clearly see that cyclist A and cyclist B do not start at the same point, because cyclist A is at the origin and B is at some y-intercept, some non-zero number. It could be 2, it could be 200, but it's definitely not 0, so they don't start at the same point. That's how we know. No, they don't start at the same point because, well, the positions are different, something to that effect. Right? And since the positions are different, we can clearly see which cyclist is ahead. And cyclist B is ahead at time 0. So this is 0. meters, if you will, but as a 0 time. They both start at the t equals 0, but they have different positions, different starting positions. Cyclist B is ahead of A. They start. So now at t equals 7 seconds, which cyclist is ahead? And here's 5 arbitrarily and 7, well, arbitrarily place them like right here. 7. And then which cyclist is ahead? Well, we can see that cyclist A is ahead of B at t equals 7. Taking a look at the graph, common sense, right? So cyclist A is ahead of B just by looking at the graph or noticing the position. That's how we know, right? Position of A is ahead of B, right? So now, which cyclist is traveling faster at 3 seconds? How do you know? So again, that's why I, introduce that definition of slope of a position time graph. The slope of a position time graph is the average velocity. So here's 3 seconds arbitrarily. Doesn't matter, we know it's somewhere before this. And we can clearly see that the slope of A is greater than the slope of B. Therefore, the velocity of A is greater than the velocity of B. That means that cyclist A is traveling faster than B. And the definition of this slope, or the relationship of slope in a PT graph. So cyclist A is traveling faster than B. Slope A greater than slope B, for example. Are their velocities equal at any time? Look back at here, and so I'll just tell you straight up that no, the velocities are not equal. I'm telling you straight up because not there at the moment, but telling you asynchronously, as it were. So no, the velocities are not the same because the slopes will never be the same. This guy's going to extend to infinity. This guy's going to extend to infinity. They'll never be the same. They'll always be that same value. So the velocities can never be equal or are never equal. Slopes constant. They don't ever get parallel, for example, so they can never be equal. If for some reason they became parallel, then the velocities would be equal. That would take an outside force, and we're not dealing with that at the moment. So what is happening at the intersection of lines A and B? Well, we see here that they meet at the same position. You can say same point, but in terms of our terminology, position, time, distance, displacement. At the intersection, lines A and B meet at the same position. So that's all these answers to these questions just by analyzing this position time graph here. I will have you do page 6, take a look at the previous graph and compare it to the new graph and answer the questions that follow. Okay. Now to our last page, page 7 here of the CVPM, 12 pages, but we're only going to do pages 1 through 7, and they need to be turned in by the end of class. I'm going to say today because you're going to see it on the day that it's due. So this needs to be turned in today by the end of class. Okay, so consider the following position versus time graphs. And what we're going to do is we're going to show rank these situations from greatest to least based on which shows the greatest displacement during the time from 0 to 10 seconds. Use greater than and equal signs whenever the less than sign. First of all, let's find the displacements and then group them together. So in graph A, we can see definition of displacement, delta x, definition equation for displacement. The final position here is the same as the initial. We say 25 minus 25. No displacement, 0 there and 0 here, same logic. So why are we saying that this is final? Because time starts at 0 and then travels on, it moves forward. So as time moves forward, let's track where the final position is. Okay, in this case, it's 10. In this case, it's 0 for the initial. So we say 10 minus 0 and plus 10. Because remember, the value of a displacement has a sign and a number. All right. And then for letter D, 10 minus 3, that'll be plus 7. And for E, 0 minus 15, negative 15. And then for F, the final position is 5, and the initial is 0. 5 minus 0 plus 5 for F. Now, you'll see that when you get to the distance, that this is going to be a different distance, because remember, distance is the amount of travel or amount of coverage. I'm trying to think of a word by saying without saying distance twice. Distance, amount of distance travel. Of course, that's not how we define terms, but the amount of ground covered, the amount of travel, something like that. Okay, so now let's group the displacements. E here is going to be greater than C. It's the next one up. So the magnitude, really, E greater than C, which is greater than D. And D is greater than F. And F is greater than both A, which equals B. Okay, so it's going to look like that. And I'll, let you explain your reasoning. It's pretty straightforward, right? Well, the values are larger from E all the way down in this order down to B. A equals B. Now, I'll just let you know as you do this part for distance, that the distance is going to be basically the same for A through E. You can see that yourself, but then F is going to be different. Then you're going to rank those as well, and then explain the reason for your ranking. That's all we're doing. So you should have already done pages 1 through 3 by last week, I believe, the last time we ended off with the CVPM. And now today, you're going to be completing pages 4 through 7 after the examples. So part 1 for page 4, and you're going to do part 2. Page 5, we did it all together. And then 6, you're going to do yourself. And then you're going to complete page 7. That's it. Pages 1 through 7 due at the end of class. And after you're done with that, it's free time. But that's all. And I will talk to you later. All right. Peace out. All right, one other thing. You want to put it on Cami, have it on the packet physically, but do your best to, if you upload it to Google Classroom as a picture document, I would prefer you to put it on Scannable. If you guys can download that app, that really helps out, because then I can just scroll through your work like this instead of zooming in and out of a picture. Cami is also works the same way. Okay, see you later.